object oriented. Object oriented. Sir, Ava.
Sir, Army.
Sir, Army.
Army. Alut Singhal. Haribhuta. Okay. Here, in this question also, I did a little editing. Calculate the work done. Yeah, calculate the work done by the turbine. Okay, Bhuta? Calculate the work done by the turbine. So here, W turbine isentropic. That is H1 minus H3 here. Okay, H1 minus H3. So we have, when we can evaluate H1 and H3 separately, you can get H1 minus H3. Okay, and this is for 1 kg. So W isentropic H1 minus H3, that is for 1 kg. So here unit may be kilojoule per kilogram. Kilojoule per kilogram. Okay, and when you have the mass flow, so W turbine isentropic, let's say this is W turbine isentropic, H1 minus H3 kilojoule per kilogram unit. So this can be converted into, let's say, mass flow rate times H1 minus H3. What happens is mass flow rate you take as kilogram per second. Now what happens is kilogram per second times kilojoule per kilogram becomes kilowatt, because that is kilowatt. The reason is kilogram cancel out and kilojoules per second remains. Let's say this is equal to kilojoules per second equals to kilowatt. So that's how. So you have to calculate mass flow rate in kilogram per hour times H1 minus H3. So W turbine isentropic here, kilojoule per kg work done. This is okay, per kg times the mass flow rate. So that's how we can evaluate this. Okay. That's how we can evaluate. So mass flow rate 4600, you can convert that kilogram per hour into kilogram per second. Okay, that is no big deal. Okay, mass flow rate kilogram per hour, kilogram per second equals mass flow rate kilogram per hour. You have mass flow rate kilogram per hour divided by, because this is 1 hour flow, then per second means you divide this by 3600. Then we can have the kilogram per second mass flow rate. Then we can have kilogram per second mass flow rate. Liters are a bit small. it bigger. Okay, this should be okay. Yeah. So this is equal to 4600 divided by 3600, 3600 seconds per hour. So this is finally kilogram per second. That is okay. This is kilogram per second. Now, how to evaluate H1 minus H3? So that is the point now. Okay, H1 minus H3. So now I have to show you the calculation, that's why. So you can have this kind of TS diagrams. Okay, it is not necessary to have this kind of TS diagram for the calculations at this time. But let's say 6 bar, anyway, this is not in bar. So here the process is something like this. As we notice it, the process is something like this. It is something like straight. So this is not the case. Something like this. Constant entropy. See down, you can see specific entropy. So it means a per kg entropy. It's the same. So high pressure, high temperature. So this is 60 bar. Is quite high pressure. So let's say if I insert the 60 bar, 400 degrees Celsius. Okay, 400 degrees Celsius. So that's how the starting point. It may be somewhere here when it comes to the actual applications of steam power plants. Okay, actual means you can see the dome here, the blue color one. We call this vapor dome. Okay, so two phase. So beyond that, okay, towards right and above, all superheated. Okay, so during the expansion, what happens is, since the entropy remains as S1 equals S2 equals S3, so what happens is here, S1, S2 and S3 is something like this. So S2 may be still superheated, yeah, let's say. So it is something like this. Please be patient. S1, S2, S3. So your S3 point is 0.1 bar, but I guess this may be wet steam. Okay, 0.1. I just put there temperature. We don't know. Okay, you have to check it somewhere. Because if we draw this table to the right scale, here this one, because here one we have no idea it is exactly 60 bar or not. We have to check this. Okay, we have to check this. 1 megapascal means how to say 1 bar is 10 to the power 5. Okay. 1 bar is 10 to the power 5 pascals. So 10 to the power 5 pascals means this is 100. So 60 bar means okay, how many megapascals? 60 times 10 to the power 5 here means this is 60 times 10 to the power 5 pascals. So 60 times 10 to the power 5 pascals means this is 6 megapascals. So you have 10 here, 1, 3, 6, 6 is somewhere here, maybe. 6 is somewhere close to here. Point 1. Point 1 is 0.1 bar means 100 kilopascals. You can check the units, huh? You can check the units. So this will come down and take here. And you have to check your temperature 400. Yeah, 400 is here. See, temperature is 400. Yeah, it is something naturally comes here. Not to say natural, your temperature 400, 60 bar here. So it is quite close. Like this, okay? And if you really have the exact, if you really have the exact, you can get the values, okay? You can get the values.
Excuse me, sir.
Yeah, Buddha.
Sir, මෙතන sir තියෙන්නේ කිලෝ පැස්කල් නේ sir තියෙන්නේ. දැන් අපිට ආවේ මෙගා පැස්කල් නේද?
Oh, megapascal.
6 මෙගා පැස්කල්.
6 megapascal is something like 60 bar, ne? Bar කියන්නේ 10 to the power 5 pascal.
5. දැන් dental physics එකේ තියෙන sir මෙතන තියෙන්නේ කිලෝ පැස්කල් වලින් නේ තියලා තියෙන්නේ sir.
මේක දීලා තියෙනේද පුතා?
ඔව් sir.
මේ red line එක උඩ තියෙන්නේ මේ black එකට උඩින් තියෙන 10 megapascal. පුතාට පේනවා නේද 10 MPa? Can you see?
Right, sir. Right.
Oh. Kilopascals. So it is something like 100 kilopascal. So I'm not going to use this graph, but even though I mention it here, I'm not going to use this graph. Yeah. Something like this, okay? Then at the time over here, you are going to use not this one, okay? You have to look into the steam table, okay? And that is what I'm expecting. So you go to steam table, it's given here. Of course, superheated, your pressure is 60 bar. You look for 60. 60 bar is here. You can see 60. Yeah. See here. You can say 60 bar in your superheated tables, and you have this line, this block. I will take it. I will take it. I will paste it here. So this is your line, okay, from the data. And you have to see where this 400 is here, okay. So if you go back to the same steam table, if you minimize this, yeah, I have to share this with the screen. Yeah? I have to share the screen with you. Steam table. See, you can see 60 here down. See, '60s here. Your pressure. Your temperature is 400 is here. 400 means fourth from the right. Fourth from the right. Temperature 400 is here. Pressure 60 is here. At 60, your saturation temperature is 275.6. So anything, the steam at here at 60, above 275.6, it is superheated. Okay, so fourth from the right. Here you have the values, so you can see the Hg value 3177. 3177. So if you go to this fourth here 3177 is the value of H1. Because here the first is the specific volume of gas, the first row. Second row is the internal energy of gas. Third is Hg. Fourth is Sg. So you have S1 and H1. Fourth, 1, 2, 3, 4. S1 is 3177. H1, S1 is 6.541. You have two values. 3177 H1. So let me put text box here. H1 is 3177 what kilojoule per kilogram. We have H1. You have to get S1 as well. The reason is isentropic expansion. You should know the entropy value at the beginning. So your S1 is 6.541. What's the unit? Kilojoule per kilogram per Kelvin. Okay, this is your S1 and H1 values. So then based on this, at 0.3, you have to get H3 value. Okay, at 3. At 3, you have to get H3 value. Okay, at 3. So this is at 1. At 1. Interesting. Okay, so at 3 you can get S3 same as S1 because isentropic. That is 6.541. That is okay, but you have to get H1. Quite straightforward to get H1 now. You go to the property tables again. I'm sharing it with you. Property tables, you have this. So pressure point 1 bar. Pressure point 1 bar. Yes, somewhere here. See, 0.1 bar is here. Okay, pressure point 1 bar. I take it. 0.1 bar. Another line here. Interesting. Yes, I put it on top. Pressure point 1 bar. You have no idea about H1, but you can get HF, the liquid phase, and gas phase. You can get HF, HG, and SF, SG. Okay, you can get those values. Okay, you can get those values. Hmm? Yes. So SF and SG and HF and SG, go back to the table again. You can say H values are the from right, the second set is H. Right, the second set. This one, this 3. HF, sorry, right from the second set. HF, HG, HFG, and HG. So your values you can see SF, so HF equals 2584. So this is HG, HG. HG at 1. Sorry, 3, HG at 3. HF is 192. Both the units, you know, kilojoule per kilogram. Kilojoule per kilogram. And your SF and SG. SF is 0.649. And your SG is 8.149. Kilojoule per kilogram per kilo. Okay. So you can see higher the pressures, lower the entropies for this case. Yeah. That's how it is. So you have this. So based on this, now you can find the X value here. The temperature, of course, you can get 45.8. Temperature is 45.8. Temperature is 45.8. See, I can fill it. The new data I put in red color maybe. See, oh, that is not red.
අපිට ටේබල් එක තමයි තාම පේන්නේ සර්.
Table is the hurry. Okay, very sorry. Yeah. Yes. Okay. And then we can pay on 45.8, the new values. Yeah. And now, based on this, you have to calculate. First, you get the X value here, dryness fraction. X, no idea. Right. You have to get that, okay? You have to get that. And from the graph here, we can say that 0.1, it straight away comes down to this vapor dome. So this is wet steam for sure. Okay, X equals what? Then you have to calculate X. Then with X you can find the H3 value. Okay, X and H. H equals what? You can try this, sir. You can try this. Yeah. Going to copy this. And I want to mention you that it is not necessary to have this table. See? No issues. This is isentropic. Okay. You just put your temperature and entropy axis, TS. Quite simple. Okay, quite simple. Quite simple. And still you can check whether this is X or it is superheated. It's still possible. Yeah. That's why it is not necessary to look into that TS graphs. See? You have this. And your TNS, your temperature, axis can be here, entropy, axis is here, okay, entropy axis is here. This is quite neater when you take this dome out, okay? And it is okay to keep the dome as well, no issues. Yeah, this is very small. SMT. Yeah. Then let's say you can see your S1 is 6.541. See how to check this. Huh? S1 is 6.541. S1 is 6.541. This is same as S3. This is same as S3. Okay, this is same as S3. Then you can check what is SF value and what is SFG. SF and SG values. SF is this and SG values. SF and SG you can take. So you can see SF and SG values. And S1 value. So when you check this one, you can feel that SF is here at 3. Okay. So at 3. S3 is equal to S1. Okay. Quite interesting. And SF and SG are these. So SF is smaller than S3. See S3. S3 is 6 point. And SG is S3 is smaller than SG. So this tells that there exists X means this is dry steel, sorry, wet steel. It is obvious. Then you calculate the X value. Let's say if you calculate X, there exists X. If you calculate X, you can take H3 as HF plus X times Hg minus Hf. So let me explain this. If you are not that familiar with this, make sure you use it. HgHf. So how to find X? So once you have H3, you go to your formulas. See, you go to your formulas. There will be W turbines. You go to your formulas and you get H1 minus H3 times M dot. Okay, you can get it. It's quite interesting. Okay. Yes. Yes, you can get this one. Okay, then your X value, that is only the X value. So how to calculate X? X is based on, okay, this expression you can write S3 equals S1 is this. Equals, okay, now this is equal to SF plus X SG minus SF. Okay, actually SG at 3 minus SG at 3 minus SF at 3. So SF at 3. So S3 is the S at 3. Okay, is equal to S1. It is this. So now you can get the solution because SF at 3, you know this. Fine. Go to the duplicate of this. Now I can substitute here. 6.541 is SF at 3 is 0.649. Plus X SG at 3 is 8.149 minus SF at 3 is 0.649. So you can get the X value. It's quite simple. You get this X, and then based on this, you can get H3 is HF. HF is 192 plus X Hg minus HF. Hg is 2584. Today it is something like I have to do this on behalf of you. You are just sitting over here and I'm doing this. But this is how you can do the calculation. So when you have H1 originally you have H1 here. CH1. CH1 you have. Now you have H3 here based on this. Now you can take H1 minus H3 and also your m dot O, the mass flow in kilogram per second, you can get it. So it's interesting. So that's how we are using isentropic concept to calculate work done, isentropic work done in turbines. But you have the X value also here. You can have the X value. So it is quite interesting. Yeah. And it is quite easy. Okay, it is quite interesting and quite easy, this one. So we need to discuss this some more. But now, yeah, we have the issues because when it comes to discussions of this nature, it is very difficult to do online, but anyway, you can analyze this. I will email you this. Also, if I'm not mistaken, I asked you to look into Coolpack software. Coolpack, that's this. Coolpack. Okay. So refrigerant utilities. Let's say you need TS curves, TS diagram, water. You look for water here. R700 something, 718. Okay. Okay, this is your diagram. Yeah. This is quite easy now. This is quite easy. You see, yes. So this is the diagram from Coolpack. So let's say, any chance to draw? This is in temperature 400, or on top here, 400 and pressure 60 bar. Pressure 60 bar. Pressure 50 here. 60 is here. Yes, that is 84. Okay. And just keep the cursor. See, you can get it. Okay. Let me draw again. I'm just drawing. Yeah? Just close only, you see. See, I can draw 0.1 bar. 0.1. Can you see the line coming down? 0.1 bar. It is something like this. 0.1 bar. Constant entropy, so it should come down straight. See, your line is here. So on top, you can get the H values, T and all. Bottom, you have the chance to get the data straight away. You can get H1 minus H3. Okay. So that is the options you are having. Okay, those are the options you are having with this Coolpack software. Okay. So see, you have the temperature values. See, whatever you can get. Plot settings. So if I go for one more, let's say cool tool analysis. TS. So you can make use of this. Actually, you can get the H values very close, and also your values you can take it here. And you can explore this. If you explore, if you can explore this, even you can plot this 1 and 3, or 1, 2, 3. Okay, you can explore. See another new one you can do. You can look for how to explore this. But anyway, this is very important. So if you have Coolpack software, no need to look for the other tables. Everything is here. You can take the data. Here down, I will show you maybe. I will take a snapshot. So down, you can see the data at any point. see down here that you can see temperature, pressure, enthalpy, entropy, even X values, you can get it there. So it's a very useful tool. Okay, so better get downloaded when it's easier for you. So let me stop the class now. If you need this, I can email you this PowerPoint. Okay, any question? Am I? Amazing. So I'm going to stop the class. It looks very silent. Did you receive the note? Hello? Tell me note Hamburg. Oh, Hamburg are there? Hello?
මේල් එකට දැම්මේ
Mail එකට දැම්මේ. Mail එකට දැම්මේ mail එකේ බලන්න මේ question එක මේකට answers ගන්න බලන්න. So after that we will discuss the essence of this. Can we ප්‍රශ්නෙන් අපි බලාපොරොත්තු වෙන්නේ යමක් ඉගෙන ගන්න. ඒ ඉගෙන ගන්නේ මොනවද කියන එක මේ කට්ටිය මේක කිව්වට පස්සේ අපි discuss කරමු. හරි. The TS diagram එක ගන්න අවශ්‍ය නැහැ. TS diagram එක නැතුව you use this slide number 13. हरने slide number 13 में use करा. Somehow get ready with the answers so that we are going to discuss. And also after that, you do 3.4 tutorial 3 question number 1. That is the last slide. Hello, so let me stop the class. Okay. Hambuna there.
ඔව් සර් ආවිල්ලා තියෙන සර්
ඇවිල්ලා තියෙන්නේ right here එක බලන්න public. So I can see both manufacturing and mechatronics students are here. So thanks for joining. So see you next week. So today looks a bit slow because of this doing this calculations, but anyway no choice, we have to spend the time. Okay, Bhuta then, let me stop the class. Bye then. Bye. Take care. Okay.